This chapter looks at how vehicle electrical systems have developed and the benefits and difficulties that it's brought about. It also looks at how engineers have sought new ways to reduce wiring while simultaneously improving features and benefits. In comparison with today's vehicles, the very first automobiles were primitive. Their designers concentrated simply on making the vehicle move under its own power. But vehicles rapidly developed, and it wasn't long before there were demands for features such as an electric starter and basic lights. Those modest requirements led to the birth of what we know today as the vehicle electrical systems. They were incredibly rudimentary, however, and comprised of little more than a battery, starter, some form of generator to recharge the battery, and a few lights. From those uncomplicated beginnings, the electrical systems of both cars and commercial vehicles steadily improved to provide greater performance, safety, and comfort. The pace of development accelerated with the advent of electronic components, such as the transistor. It enabled the introduction of systems such as contactless ignition and electronic fuel injection. But it was the integrated circuit, or microchip, which probably led to the biggest acceleration in development. Since then, electronic components and microprocessors, which are really tiny computers, have been used extensively, and today virtually all systems are electronically controlled. Electronics brings huge advantages such as greater and more accurate control, rapid response, fewer moving parts, simplification of complex systems, opportunities for self-diagnosis, and the chance to develop new systems that were never thought possible in the past. Nevertheless, although management systems have brought many advantages, they've increased wiring, connections, and added weight and complexity. It was because of the huge increase in wiring during the 1980s and 1990s that engineers began looking at ways of simplifying circuits. Before the digital network revolution, management systems such as those for the engine and transmission were self-contained and were busy with their own tasks. This meant that the control module received information from its own dedicated sensors and activated its own specific actuators. This arrangement became problematic as new systems were introduced, as it resulted in the duplication of sensors, even though each system often required the same input information. For example, the SK commercial vehicles used up to 6 separate coolant temperature sensors to supply various control modules, including the instrument cluster. This was costly and made wiring complicated. Furthermore, as more management systems were introduced, the number of control modules increased correspondingly. Do you know how many control modules are fitted to the current Mercedes-Benz S-Class, or Actros for instance? The S-Class uses about 40 control modules to control everything from the engine and gearbox through to the central locking, air conditioning and the lights. The Actros uses up to 25 control units to manage its highly developed engine and running gear technology and advanced driver information systems. In the future, it's likely that even more electronic systems will be required to meet increasing environmental demands and customer requirements. We saw with the SK truck, for example, how systems working independently increased components, wiring and weight. Engineers realized that if control modules could communicate with one another, it would bring significant advantages. This led to the development of digital networks, enabling control units to talk to one another in real time and share information. Digital networks enable the signal from a coolant temperature sensor, for instance, to be used by several different systems. The signal from the sensor supplies the first control module, and from there it's distributed to the other modules. Moreover, the cables that link the control modules together can be utilized to transmit other signals as well, making it very efficient. So, networking systems together has brought significant improvements in communication, whilst reducing wiring, saving weight, and simplifying operations. This chapter looks firstly at bits and bytes, which is the basis of all digital communication. It then describes the different speeds and ways of transferring data. Digital communication is the basis of all networks and provides the technology used within control modules. So, what is digital? Well, digital actually comes from the Latin word digitus, meaning finger. Unlike analog, which can mean variable, in digital terminology there are only two states, a 0 and a 1. In electrical terms, this is equivalent to off and on. These zeros and ones, or off and on signals, form the communicating language in computers and control modules. So, as intelligent as these devices are, they can still only understand simple on-off commands. By grouping 0 and 1 signals together, they make coded messages that communicate a massive amount of information to and from control modules. The smallest unit of digital information, which is a single on or off signal, is called a bit. The word bit, incidentally, comes from binary digit, which is the basic unit of measurement in the binary system. To help understanding, 1 bit is represented here by a light bulb. Let's say that if the light is off, it's a 0, and if the light is on, it's a 1. By adding a number of bits together, a larger code can be constructed, enabling more information to be sent. By adding more bits together, more complex codes can be made up to convey more information. Do you know what 8 bits are called? 8 bits are called a byte. In reality, the messages that travel every second between control modules are made up of many 1/1000ths of bits of information. The messages, arranged in bytes, convey data around virtually every system on the vehicle. Generally, we don't talk about thousands of bits of information. We put them into metric units, just like any other items. For example, 1,000 bits is known as a kilobit. So 20,000 bits is equal to 20 kilobits, and so on. And 1 million bits is known as a megabit. It's very unlikely that you will ever need to convert values in your normal work, but just for interest, try this puzzle. Occasionally, instead of kilobits and megabits, you will see the expressions kilobytes and megabytes. Well, firstly, there are 8 bits in 1 byte, 1024 bytes in 1 kilobyte, and 1024 kilobytes in 1 megabyte. To summarize, it can be said that digital technology converts information signals into on-off codes for rapid and accurate transfer of data in and between control units. You may have heard the expressions serial and parallel communication. With serial communication, control modules are linked together, for example, by a single data line. In serial communication, the bits travel along the line one after the other in series. With parallel communication, however, multiple data lines are used to connect between control modules. As you see, with control modules connected this way, the bits can travel along separate parallel data lines all at the same time. This is the method used by most computers to transmit data to printers, for example. The advantage of parallel communication is that it's faster. Its disadvantages, though, are that it needs more wiring, which increases connections, costs and complexity. With serial communication, it has the advantages of less wiring, fewer connections and being less complex. The only real disadvantage is that, when compared to parallel, it's slower. Nevertheless, serial communication provides more than sufficient speed for vehicle application and is therefore used extensively. With serial communication, you also need to be aware that there are different methods of sending the digital bits along the cable. It's similar to spoken languages. If people speak different languages, then they can't communicate. But if they speak the same language, then they understand each other perfectly. The difference is that with control modules, their language is known as protocol. Just as different languages have evolved throughout the world, there are also various ways of transmitting digital data. Here are two examples: the K-line and the fiber optic systems. Another way of transmitting data is using light pulses passing down fiber optic cables, as is used in the combined audio and navigation system of some passenger car models. Depending upon the vehicle type, the serial K-line is used for communication between certain systems. For example, the star diagnosis tester uses it for self-diagnosis purposes. The protocol of the K-line is different to that of the CAN bus system, which we'll be looking at in another chapter. In addition to different ways of transmitting data, there are also different speeds. The fiber optic system used in the passenger car audio system is known as D2B. It can transfer data at a very high speed of up to 5.6 megabits per second. The K-line system has a data transfer rate of 9.6 kilobits per second. So why use different data transfer rates? Well, for the audio system to reproduce excellent sound quality, it must be capable of transmitting a lot of data rapidly, so that the D2B fiber optic system is utilized. In comparison, the K-line operates slower because it's transferring less data, and it isn't a problem if it arrives a few milliseconds later. Furthermore, generally, the faster the communication, the more expensive the components. It's therefore sensible for manufacturers to choose the most suitable components for the specific application. This chapter looks firstly at the meaning of the word CAN bus. It then explains how CAN bus functions and its advantages and the purpose of the CAN high and low cables. The construction of the messages, known as data telegrams, and the function of the terminator resistors is also explained. So what does the term CAN bus mean? CAN is the abbreviation of the English words Controller Area Network. Network simply means a number of control modules linked together that can communicate with one another, similar to a computer network. The term bus, which generally follows the word CAN, refers to the cables that join the control modules together. The CAN bus system consists of a number of control modules connected generally by two cables that transmit data between the modules, often called a data bus. In some commercial vehicles, you'll also find 4-cable CAN systems. We explain later why and where these different systems are used. The CAN bus system also allows the vehicle manufacturer to relatively easily add control modules to an existing network, offering greater flexibility for system designers. The German company Robert Bosch developed the CAN system and its protocol for use in the automobile industry. The protocol conforms to international standards known as ISO. As a result, control modules built by other manufacturers can communicate via the network, providing they conform to the same ISO standard. Mercedes-Benz first used CAN in 1991 in the 124 model, where it linked the engine management and automatic transmission systems together. CAN is simply a communication system, but it has many advantages compared to other communication systems. This graphic symbolizes a simple CAN bus system. Most control modules both receive and transmit messages. The signals from sensors are used not only by the individual module, but are converted into CAN messages that are then distributed via the data bus for use by other modules. The modules are also sufficiently intelligent to wait until the network isn't too busy before sending a message. All modules receive the messages. On receipt, each module checks to determine if the message is relevant. If the message is relevant, the module accepts it, checks it for errors, and then processes the information. Those with errors are aborted and are automatically retransmitted. Messages that aren't relevant are simply ignored. This method of message distribution means that once a signal from a sensor is on the data bus, it can be used or ignored by any module using the network. As a result, wiring is reduced and communication between systems takes place in a fraction of a second. In the previous example, there was just one message, but normally there are lots of messages. For this reason, they're sent in order of urgency. If two control modules try to transmit at the same time, then an arbitration technique ensures the messages are sent and received in order of priority. Here, for example, are 3 messages of different priorities, all of which are required by control module D. One message contains high-priority braking information, whilst others could include data about temperature or air conditioning, for example. Here, red represents the highest priority and green the lowest. As you see, the messages travel in order of priority, which is a unique advantage of the CAN system. You'll find out more about how the messages are made up later. The fact that the messages are received by all control modules, whether they're needed or not, is another benefit of CAN bus. We explained earlier that other control modules could be added to an existing network. The PSM system fitted to some commercial vehicles is a good example. PSM, which stands for Parameter Able Special Module, permits body and trailer manufacturers to fit specialist systems and equipment relatively easily without installing lots of extra wiring and switches. If the additional equipment, such as that used by a refuse vehicle, requires road speed, engine start, or parking brakes information to function, then those signals are already available on the CAN. All that's required is for the PSM to be programmed to recognize and respond to the necessary signals. In this way, the PSM, together with the CAN, greatly simplifies the installation of additional systems. To reduce the risk of interference from spark plugs, solenoid valves, mobile telephones and radio transmitters, for example, the CAN system uses a minimum of 2 cables. Sometimes, to provide further protection against interference, the cables are twisted. The messages are transmitted along both cables simultaneously, but are inverted to one another. During processing, the potential difference between the 2 signals is compared to interpret the result. This arrangement makes it unnecessary to distinguish between valid and spurious signals, since by induction, an interference signal would result in a voltage increase on both cables simultaneously. One cable is known as CAN high and carries the signal that rises when it's on. The other cable, CAN low, is a mirror image. When the signal is on, the voltage is pulled low. Incidentally, the off part of the waveform is not normally set at 0 volts. This enables the module's self-diagnosis function to differentiate between a normal off signal, a short circuit, or no signal at all. When viewed on an oscilloscope, the waveform looks slightly different to the graphic. Here's an example of a CAN waveform captured from a vehicle using the Star Diagnosis Herman measuring system. Note that depending upon the vehicle and how the oscilloscope is set up, you will see slightly different waveforms, but you'll learn a lot more about that later. The CAN messages, often called data telegrams or data frames, contain specific fields of data. The data telegram contains 7 fields. Here each field is represented by a different colour. The start field marks the start of the message and consists of a single bit. The arbitration field, which is 12 bits in length, defines the level of priority, contains the identifier classifying the content. The control field consists of 6 bits and specifies the number of bytes in the data field. This field allows any receiver to check whether it's received all the information. The data field contains the actual information and includes up to 64 bits. The purpose of this so-called cyclic redundancy check field of 16 bits long is to detect errors. The acknowledgement field is 2 bits long. The receivers of the message report to the transmitter that they've correctly received the data telegram. If an error is detected, the transmitter is told to send the message again. The 7-bit end of frame field marks the end of the message. Note that after the end of each data telegram, there's a 3-bit intermission before the start of the next data telegram. Here's the graphic representation of a CAN network that we showed you earlier. Well, at some point in the circuit, terminator resistors are normally fitted that bridge the CAN cables. They combat reflection signals that occur naturally in cables carrying high frequencies, resulting in interference. Reflection signals can cause a similar effect to those which often occur in a TV antenna cable. Without a terminator resistor across an open aerial socket, the picture can develop a ghost appearance. Installing a resistor removes the reflections, improving the picture. The terminator resistors are integrated into the star point connectors of the 24-volt commercial vehicles. In addition, they often have ferrite coils for voltage stabilization. In the cars and 12-volt commercial vehicles, the resistors are within a control module located at the end of the network, such as the engine control module or the EZS ignition key module. This chapter describes the different CAN bus versions and briefly looks at CAN bus voltages and gateways. Depending upon their function, not all control modules need to communicate at the same speed. Networks handling systems such as central locking, electric windows, auxiliary heaters, air conditioning and so on need not communicate as fast as those of the engine and braking systems. Therefore, separate so-called high and low-speed CAN systems operating at different speeds are used in both passenger cars and heavy commercial vehicles. However, note that in the Vito and Sprinter light commercial vehicles, only a high-speed CAN is used. In the base specification models, it links the control modules of the engine, ABS, instrument cluster and immobilizer, for example. Now you can find out about some of the systems that use high-speed CAN systems. As an example, this graphic shows the modules that are part of the high-speed 500 kilobits per second network of a C-class vehicle. Here's a graphical layout of the high-speed 500 kilobits per second network of an Actros heavy commercial vehicle. Now you can find out about some of the systems that communicate via low-speed CANs. Remember that the light commercial vehicles only have a high-speed CAN. As an example, this graphic shows the modules that are part of the low-speed network of a C-class vehicle. However, before you explore the low-speed CAN, here's an interesting point to note. A feature of this particular network is its sleep mode, designed to conserve battery power after the vehicle has been left unattended. Approximately 30 seconds after the ignition is switched off, and there's no activity on the data bus, the network goes into sleep mode, whereupon it consumes negligible current. However, when certain items are operated, such as the central locking, the network wakes up and switches back into working mode. You may have noticed that a few components, such as the electronic ignition switch module and instrument cluster, appear in both the high and low-speed networks, but we'll explain about that later. Here you can find out which control modules of the heavy commercial vehicles communicate via low-speed CAN systems. In general, low-speed CAN systems are favoured for communicating over longer distances, such as for trailer functions and so on. You may have noticed that unlike with the cars, in many instances modules using low-speed CAN systems are not connected together by an independent network. Instead, they communicate with each other using the high-speed network via a special item called a gateway. Gateways are incorporated within specific modules, and we'll explain about them later. Some of the low-speed CAN systems operate at different speeds too, ranging from 125 to 250 kilobits per second. As we've already explained, most CAN systems communicate via a two-cable data bus. However, on the heavy commercial vehicles, some modules are linked via a four-cable data bus instead. Depending on the model and system, the two extra cables provide additional protection from interference and are connected to ground. Or they provide the permanent live and ground supplies for the control module to which they connect. The operation of the CAN, however, is unaffected. In another chapter you saw a CAN waveform on an oscilloscope. It's important to note that the switching threshold, that's the difference in voltage between the top and base of the waveform, is not always the same. It varies according to the vehicle and the speed of the CAN. For example, on this passenger car high-speed CAN, the base of CAN high is at 2.5 volts, and the switching threshold is 1.1 volts. CAN low, therefore, switches between 2.5 and 1.4 volts. Note that the voltages of the low-speed CAN on the same vehicle would probably be completely different. In the Actros commercial vehicle, the base of CAN high on one of the low-speed CAN systems is set at 12 volts. The top of the waveform rises to 16 volts, which is 2/3 battery voltage. CAN low is a mirror image, of course. If you were to view another network on the same vehicle, you would find other voltages and waveforms. It really depends on the particular version. Generally, the reason for the voltages being greater on low-speed CAN systems is that it's better for data transfer over longer distances. Nevertheless, it's unnecessary to try and remember the voltages or worry about them, because the STAR diagnosis includes a number of comparative waveforms for reference. These so-called reference pattern pictures can be selected to compare against the live waveform. Sometimes control modules on a high-speed network need to communicate with those on a low-speed network and vice versa. In the passenger cars, for example, the central locking system and radio, which are part of the low-speed CAN, require row-speed information. This information comes from the traction control module, which is part of the high-speed network. To enable the exchange of data between the two networks, a gateway is used. Acting as an interface between the networks, the gateway adjusts the speed of the data protocol and the voltages from either network to allow the sharing of information. The gateway is software-based and is integrated within specific control modules. In the passenger car CAN wiring diagrams, modules incorporating a gateway are often identified by double-ended arrow symbols. This particular diagram is for an S-class vehicle. This chapter explains about identifying the different CAN bus networks and the identification of the CAN cables. It also shows the location of some of the CAN connectors. In the passenger car wiring diagrams, the terms high and low-speed CAN systems are not used. Instead, you'll find the names engine CAN and interior CAN. The engine CAN is the high-speed CAN, and the interior CAN is the low-speed CAN. In many of the wiring diagrams and in other literature, the terms CAN-B for the interior CAN and CAN-C for the engine CAN may also be seen. The designations H and L near the control module connections simply identify the CAN-high and CAN-low cables. In the heavy commercial vehicles wiring diagrams, unfortunately, you can't determine which are high or low-speed networks. However, it's sufficient to be aware that the low-speed CAN bus systems simply link individual control modules to those which are part of the high-speed network. In the commercial vehicles, the CAN cables are best identified by their colours. On the 24-volt models, irrespective of whether it's a high or low-speed network, the CAN high cable is generally blue. The CAN low cable is yellow. In the light commercial vehicles, such as the Sprinter, CAN low is usually green, and the CAN high cable is green and white. In the passenger cars, with the exception of CAN-C, the cable colours vary slightly depending on the model. Here, as an example, you can find out the colour of the cables on these two models. The CAN wiring looms are often joined at strategic points around the vehicle. On the heavy commercial vehicles, the high-speed CAN cables join at a star point, shown in the diagram like this. In the vehicle, you'll find them usually in the cab near the fuse box. They also incorporate the terminator resistors. In the light commercial vehicles, such as the Vito and Sprinter, the cables meet at crimped connection points, known as J-points within the wiring looms. In the passenger cars, for example, the CAN cables are joined at special connector blocks situated around the vehicle. The locations for the connector blocks depend on the model. This illustration, for example, shows the locations for the connector blocks in a C-class. In the C-class, there are 4 in total. In the engine CAN of some passenger cars, you will also find crimped Z-point connectors in the wiring harness, similar to the J connectors of the light commercial vehicles. This chapter looks at the logical fault finding that can be applied to CAN bus systems. To assist with CAN bus fault diagnosis, the control modules include extensive self-diagnosis features that can be accessed using DAS. Remember also that the CAN wiring consists of only 2 or 4 cables, which when isolated from the rest of the network can be tested using a multimeter like any other electrical cables. Moreover, because different systems using the network send their messages along the same cables, it often makes logical fault diagnosis a little easier. Let's consider, in this passenger car example, a fault where the central locking system does not work. By studying the wiring diagrams and having a basic understanding of the system, it can be established that the central locking system, and for example the electric windows, use the same CAN. What could you do next to check simply the function of the CAN cables? If the electric windows function correctly, then the central locking fault can't be due to a defective CAN system, as it's utilized by both systems. The CAN cables can thus be eliminated from the investigations, and fault diagnosis can be focused on the central locking system. Let's consider a fictitious fault on an Actros where the temperature gauge doesn't work. By studying the wiring diagrams and having a basic understanding of the systems, it can be established that the rev counter and temperature gauge both receive their information from the MR control module via the same CAN. Preliminary checks have also established that there are no fault warnings displayed. So now try this question. What could you do next to check simply the function of the CAN cables? If the rev counter functions normally, The CAN system can't be the cause of the temperature gauge fault because both instruments receive their information via the same network. Therefore, fault diagnosis can be focused on the temperature gauge circuit. Using the logical approach to fault diagnosis will help you in finding the cause of most electrical problems, including those associated with CAN systems. So noting these key points should help you and can be applied to most situations. First, check all systems for correct operation. There may be other items on the vehicle that aren't working, which could help you in localizing the fault area. Make a visual inspection to check for obvious damage or dampness, which is often the key cause of electrical problems. Interrogate all system memories to check for any stored faults, and where possible use the STAR diagnosis DAS software. It's specifically designed to guide you through the fault diagnosis of most systems. Finally, analyze all the information you've gathered, together with the wiring diagrams to help you plan a work procedure. And above all, think before dismantling anything.